In this tutorial, we'll be discussing the history of the atom, specifically the atomic theory. The prehistory of the atom, we were making tools from various materials, such as bones or stones. Then we discovered fire, which is combustion, and then we were able to start cooking. In approximately 10,000 BC, we started brewing and fermenting. And around 4,000 BC, we started metallurgy and making bronze. We didn't really know what was happening or why it was happening. We just knew that it was helping us. Then, once we get to 6 BC, or through the 3rd century BC, we started creating a theoretical model for the modern world. This is not based on religion or myth. There are 4 primary elements: fire, water, earth, and air. They're used to explain properties. For instance, water is cold and wet, but when it's heated, the water is evaporated and turns into air. This is based on speculation. Approximately the 5th century BC, Democritus and Leucippus came up with our original version of the atomic theory. They came up with the word atom by the Greek word atomos, which means indivisible, which means you can't break it down. The original theory says that matter is composed of atoms separated by empty space in which they move. Atoms are solid, homogeneous, or uniform, unchanging, and individual. All changes in matter are due to changes in these atom groupings. And different kinds of atoms differ in shape and size. Properties of matter reflect these properties of the atoms. Again, you can't test it. This was just based on speculation because they didn't have the proper equipment. Then over 1,500 years passed, and we get to the Industrial Revolution. And this is the development of the precise measuring instruments that we can actually do true reactions. We also developed the metric system, or the SI unit system. And it's the birth of our true science. In this period, in 1661, an English scientist named Robert Boyle determined there were problems with the Greek model of the elements. For one, you can't extract from these substances, and you can't use to form other substances. So Boyle determined a new definition of the element. He stated that any substance that can't be decomposed into simpler substances by a chemical reaction would be considered an element. And a compound contains 2 or more of these elements. In 1789, Antoine Lavoisier started looking at something called the law of conservation of mass. And he states that a chemical reaction, that matter is neither created nor destroyed. The atoms are rearranging, so the atoms that are there at the beginning are still at the end, they just look different. Therefore, because the matter is still there, because the atoms are still there, the mass is the same at the beginning and the end. The mass won't change either. Here's an example. In this test tube, we have silver nitrate, and in the flask, we have sodium chloride. Notice the mass is 300.23 grams. When the flask is tipped upside down, the silver nitrate goes into the sodium chloride solution. Notice that the volume went up, and now the test tube is empty. If you look really closely, you can see little white flakes in here. That's white precipitate from the silver chloride. According to Lavoisier, the mass at the beginning will be the same at the end as it is. That's because the atoms, even though they look different, they're not the same. They've changed places. For instance, silver nitrate, that silver is now with the chlorine to make silver chloride. Both the silver and the chlorine are still there. They're just with each other rather than the original atoms. Joseph Proust came up with the law of definite proportions, and he's saying that all samples of a given compound, regardless of their source or how they were prepared, have the same proportions of the constituent elements. We're looking at mass ratios here. and this led to the difference between a compound and a mixture. So let's take a look at the law of definite proportions. In a 100-gram sample of water, 11% of that mass is going to come from the hydrogen. So 100 grams, we change that percentage to a decimal by dividing by 100. So times 0.11. That comes out to be 11 grams of hydrogen. That means the remainder of that, which is 89 grams, would then be the oxygen. Here's another example. If we have 3% of a 100 gram HCl solution is hydrogen, so that means 100 grams times 0.03, because I changed the percentage to a decimal by dividing by 100. That comes out to be 3 grams of that HCl solution is hydrogen. What's the mass of the chlorine? Well, the chlorine would be the remainder of it. So 100 minus 3 is 97. Now, I had stated that the law of definite proportions came up with the mixtures and compounds. Mixtures does not have the constant composition. So intensive properties such as density vary with the composition. Depending on how concentrated it is, it might have a heavier density. It contains 2 or more elements and or compounds that can be separated, purified by physical processes such as heating or hand sorting. Pure substances, however, include compounds and elements. They're a fixed set of intensive properties. So that means once the density is determined, it doesn't matter how much you have, it's always going to be the same. And they obey the law of constant composition. Now, John Dalton in 1804 came up with the law of multiple proportions. When 2 elements, let's call them A and B, form 2 different compounds, so we're saying like maybe it's A2B3 or A2B, they still have the same elements, but the ratios are different. The masses of B that combine with 1 gram of A can be expressed as a ratio of small whole numbers. So different compounds, even though the elements are the same, will have different ratios. Let's do an example of this. Nitrogen forms several compounds with oxygen, including nitrogen dioxide and dinitrogen monoxide. Nitrogen dioxide contains 2.28 grams of oxygen for every 1 gram of nitrogen. So that's where we're focusing the 1 gram. While dinitrogen monoxide contains 0.570 grams of oxygen for every 1 gram of nitrogen. So we're comparing, both of them are comparing their masses to nitrogen. Now we're going to compare them to one another. Show that these results are consistent with the law of multiple proportions. So 2.28 grams of oxygen for every 1 gram of nitrogen and 0.570 grams of oxygen for every 1 gram of nitrogen. This should come out to be a whole number ratio, and it does. It comes out to be 4. This then had John Dalton thinking about the atomic theory, and he came up with a new atomic theory. Dalton proposed a theory of matter based on it having ultimate indivisible particles to explain these laws. And this is his theory. Please note that not all of these are considered to be 100% true, because we've done more research and we've gotten more exact results. Each element is composed of tiny, indestructible particles called atoms. The reason why I said that they're not necessarily true, indestructible, we have atomic bombs. We know that we can take things like the protons and neutrons out of the atom with a lot of force, but it can be done. So they're not indestructible. All atoms of a given element have the same mass, which is also not true because we have isotopes and other properties that distinguish them from atoms of other elements. Atoms combine in simple whole number ratios and to form molecules of compounds, which we know are true. In a chemical reaction, atoms of one element cannot change into atoms of another element. That's called a nuclear reaction, not a chemical reaction. They simply rearrange the way they are attached. So even though we have a couple errors in his atomic theory, it gave us one step further so that way we can do more experimentation.